that you can do this next step. And it's also important that you understand the logistics of it. First off, you got to know what a rational number is. And a rational number, by definition, is any number that can, notice I'm focusing on this word can, doesn't mean it has to be, it just means it can be written in the form of a over b, where both a and b are integers. So in order to be a rational number, you have to be able to write it as integer over integer. And if you remember the set of integers, it's this set right here. -3, -2, -1, 0, 1 to 3, on to both infinities. So as long as you could write the number as an integer over an integer, you have what we would call a rational number. Give me an example of a number that's rational. Zach, was that you? Okay, well, I'm calling on you now. 2, outstanding example. That's rational.
0.1.
0.1 repeating, right? That's rational. Give me a rational number. What is it? 1/6. That's rational. What else? What other numbers are rational? 3. That would be like 2. All the numbers that are like 2, 3, 4, 5, all rational. Absolutely. Is not. Can you write it as an integer over an integer? If you can't do that, it's not rational. What else is rational? Hey, I'm just throwing it right there, thanks. What else is an example of a rational number?
Negative.
Negative. Sure. Any number that's integer over integer negatives, absolutely rational.
What's squared?
Well, you didn't give me a number, you gave me something with an operation. So when you square 1, you get 1, so yes, absolutely 1 squared. But I want a number, not something that I have to do to a number.
Would pi be rational?
It would not. You have to be able to write it as an integer divided by an integer.
So 22/7.
It's an approximation of pi.
Okay.
It's just an approximation. How about the square root of 4? It's under a radical, it's not simplified. It's kind of like 1 squared. But square root of 4, that would be okay. So examples of things that are not rational, obviously we have had pi and I. 0.12, 112, 111, 2, on to infinity like that would be not rational. Repeating decimals, this is repeating. 0.1 is 1/9. That's integer over integer. 0.33333 repeating is 1/3. Square root of 7, not rational.
Is E irrational?
He is also irrational, but nobody but you probably knows what E is, maybe a couple other people, but we haven't done E yet.
How about a number divided by 0? Like 3?
That's not a number. Integer over integer, dividing by 0 is an undefined expression. It's a good idea, but it's not a number, so it's not rational.
What about infinity?
Infinity is not a number either, it's an idea. Infinity is a concept that we approach, but we can never attain. It's just an idea. Again, really good thought for this, but not irrational or irrational in that case. What else? Anybody think of anything they don't know if it's rational or irrational? If it's a finite decimal, 0.125, that's good. Any decimal that ends is automatically rational.
What about a number to a power?
Well, again, he brought that up, and absolutely good idea. What would you get when you took the number to the power? That's probably or potentially going to be irrational. Just depends what power and what number you started with. So even like this, I'm saying like square root of 4. What is square root of 4? That's 2. So I've given that answer twice in there. So it's really what happens after you do the operation. Now, square root of 7, I can't simplify that anymore. If I try to make it a decimal, it's non-repeating, non-terminating. Okay? We are only going to be concerned with these numbers right now, and in this process that we're doing today. Okay? This is the rational zero theorem. It is not the zero theorem. It is not the any number theorem. It's not the whatever you want for zero theorem. It's only the rational zero theorem. Now, any polynomial written in descending order with integral coefficients the degree n will tell you how many roots there are. The degree tells you how many roots there are. Some polynomials don't have any rational roots, but most do. If a polynomial has a rational root, what we're telling you in the rational zero theorem, the rational root theorem, is that any potential rational root has to be from the set of p divided by q numbers. P are the factors of your constant term, a sub 0. Q are the factors of your leading coefficient, a sub n. Got to be in descending order now. And again, I am not telling you that P over Q is a rational zero. I'm saying it's possible that it's a root of that, of this polynomial. And if none of your P over Q's work, then you don't have any rational zeros. Now there are a couple of little tricks to this, but by and large, as long as you understand that P are all your factors of the constant, and Q are all the factors of the leading coefficient, then you take all the P's and put them over all the Q's, and those are your potential rational roots. All right? What you're looking at is Match.com. These are the potential people that we have that would match with you. I'm not saying that these people are going to match with you, but if anybody in our data system is going to, it's going to be these people. All right? So, how do we find out what the rational roots are? Every time we go through this, people say, oh, this is so hard. Not the right word. This is so tedious. It's kind of a pain in the butt. It's time consuming. But level of difficulty is a 0.1. It's easy. You just have to be willing to try it. I haven't asked a question, but if you want to ask one and answer it, knock yourself out. What's happening?
I thought you just asked how you find, like, how you do this.
No, I haven't. Oh. You're trying to steal my whole lesson, aren't you? Out of the way. Look at this polynomial function. How many zeros are there? 3. Does anyone not understand that there are 3 roots? Okay? What's the highest power on your variable? That's called the degree, right? The degree tells you how many roots there are. Now, again, there's 3 roots. Maybe none of them are real. Maybe none of them are rational. Okay? We don't know. I mean, I know a little bit more than you know at this point. But I'm telling you, we don't know for sure. But if there's a rational root of the 3, they have to be made up of the list from your P's and Q's. So here's what I'm going to ask for work from you. Your P values have to be factors of the constant. What are the factors of 20? Okay, you got exactly half of them. Plus or minus. So when you make your list, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Did I miss any? Sometimes you miss one when you're going through. You're looking at the numbers that multiply to give you 20. And make sure you take both pluses and minuses. Then I want you to list out the q's. Q's are the factors of your leading coefficient. Your leading coefficient in this problem is 1. So that makes the q list easy, plus or minus 1. The fewer factors there are for p and the fewer factors there are for q means the fewer factors there will be for p over q. Is everybody with me on p's, q's?
So Q is Q, right?
Q, no, Q are the factors
The one, yeah.
of your leading coefficient. In this case, it's just a 1. If there was a 2 here, you'd have plus or minus 1, plus or minus 2, and so forth. So in this case, your P over Q's are the same as your P's. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Now, I would strongly encourage you to have a good eraser, and I would encourage you to have a pencil and a pen to do the rest of the work. It just makes life easier. These are your potential rational roots. If they're your potential rational roots, we're going to find out which one it is by synthetically dividing. 1, -8, 11, and 20. What are we shooting to get? 0. If we got a 0, we knew we would have a root, and therefore we would have a factor. So if you wrote this stuff in pen, then you can erase when it doesn't work. And you can stop as soon as you know it doesn't work. So I'm going to just start with 1. And we're going to synthetically divide 1. So we have 1, 1, -7, -7, 4. That's not going to do it. Then you can just go back here and erase. And we don't have a positive 1 as a rational root. Then you try -1. 1, -1, -9, 9, 20, -20. Hoorah! Only had to do 2 and got me 1. It's like fishing. If you have a third-degree polynomial, through your guess and checking, you only need to find 1 root by doing the P's and Q's. You only need to do 1 because your quotient will be a quadratic. Set that equal to 0 and solve. When we solve this, you're going to get x minus 4 and x minus 5. So x could also equal 4 and 5. You now have 3 solutions. 1, 2, 3. Which means your graph has zeros at -1, 0, 4, 0, and 5, 0. Now, sometimes this becomes an exhausting list, and you have to keep trying and trying and trying. You'll see that we'll get fractions that can be in there. You have to be able to work them through. When you graph this polynomial, it's going to go through -1, +4, and +5. You don't have to worry about graphing today. I just want you to see that that's where they cross. Here are the components again. The degree tells you how many you're looking for. P is the factors of your constant term, in this case 20. Because -1 gave me a 0. Okay? Q are your factors of your leading coefficient, and then you take all the p's over all the q's to get your p over q list. Then you can randomly select, you can start small, go big, whatever you want, and synthetically divide your p and q, p over q values until you get a 0. Okay? If you start with a degree 3, you only need to find 1, then you're going to use quadratic formula, factoring whatever you want to find the other 2. If you have a degree 4, which we'll do in a minute, you have to do more than 1. Before we go on, let's see. Anybody have any issues? Degree, P, Q, P over Q, and then synthetic division.
So what you did was you divided to like that list, right?
You take your P's, write them over all the Q's, and that's the list of P over Q's. It'll be making more sense when we have a better list of Q's.
What would happen if it was like not 1x to the cubed on top? Like if it was like a 2 or a 3?
Well, if it was 2, it's quadratic. You would just factor it. You don't need to do P's and Q's.
That's true.
Cubics, we're not very good at factoring. The only way we could factor it is if they were grouped in something in common and we got lucky,
Right.
which just isn't going to happen that often.
Right.
Even though this is factorable, you just don't have that ability to factor it. Neither do I. So we P and Q it. It factors. We know how it factors. It factors to x plus 1 and x minus 4 and x minus 5, but we're never going to be able to do that.
Right.
But P and Q's in the rational root theorem, that tells us where they have to be if they're rational. Okay? Right?
Isn't there 4 of them? So you couldn't do the
4 of them.
of the terms.
There are 4 terms. You mean like here?
Yeah. So couldn't you do the factor by?
You can, but there's nothing in common here except x squared, and there's nothing in common here. So you have x minus 8 and 11x plus 20. They're not the same. You're absolutely right. But as I said, most of the time, no, it's not going to be nice. It's just not going to work out. Okay? This one is degree 4. Okay? This is degree 4, which means 4 roots. 4 x-intercepts. What do you know about the end behavior of this? Up and up. Degree is 4, leading coefficient is positive. Okay? See if you can list all the p values. And see if you can list all the q values. And then don't worry about the p over q. We'll do that together. But right now, list your p's and list your q's. List your p's, list your q's. See if you can make that list happen. No? You shaking your head no? Yes, you are. No, you know. You don't know if you're shaking your head no? Killing me, dude. You got the Q's already, though. Why not the P's? Oh, it doesn't matter. Still plus or minus 7. Because 10 is negative, that has no impact at all. It is a negative 10, but you can have a plus 1 and a minus 10 to get there. So yeah, don't let that bother you at all. How many P factors were there?
4.
Come on now. Right? What are they?
Plus minus 1, plus minus 2,
So there's 8. And now this time with your Q's, you weren't so lucky. Plus plus or minus 1 always. What else? So now when we do our P over Q list, you do all the P's over 1, which means you're going to have plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Then you do all of these over 2. Plus or minus 1 over 2, we have to include that. But plus or minus 2 over 2, we don't. Because what is that? That's 1. We already have it. Plus or minus 5 over 2, we have to include that. Bless you. But plus or minus 10 over 2, we don't need to include that. Because that's 5. Does everybody see that? All of these P's over 1 give you the first row. All of these P's over 2 gives you this row. We don't have to repeat. And then all of these over 4 gives you plus or minus 1/4. 2 over 4 is going to give you a half again. 5 over 4 we need to include. But 10 over 4 is the same as 5 halves. It's still not a very fun list. That's a lot of numbers, 16 of them. And this time you need to find 2 of your zeros, not just 1. And how you find the second one is very important. All right, so let's take a look. We have 4, -1, -3, 9, and -10. And we're shooting to get ourselves a 0. Okay? Is everybody with me at this point? If you're not, this is a really good time to stop and redo it. I mean, I don't have any problem going back. I want to make sure you guys are nails with this, because if you get this, the rest of the chapter falls into place so nicely.
I don't get how you found the values of like the P and the Q.
The red ones?
Yeah.
Okay, so here's my list of P's.
Okay.
I'm literally going to put them over each of these Q's.
Oh.
So let's take the first Q as 1. Anything divided by 1 is what you started with, right? That's the first row.
Okay.
Now I'm going to use the Q value of 2. So I'm going to put each of these P's over 2.
Oh.
Are you seeing that?
Yeah.
So you get 1/2. But 2 over 2 is the same as 1. We already got that.
Okay.
And then 5 over 2, we got to include that.
All right.
And then 10 over 2 is the same as 5. I've already got that.
I see.
All right.
Okay. And then you do the same thing with 4.
And then you do the same thing over 4, and the ones that reduce, like 10 over 4 is the same as 5 over 2. I don't need to count that.
I see.
Okay? This red list, both rows, are really what we're going to choose from.
All right.
Okay? Somebody else have a question? So now, your guess is as good as mine. All right? So we're going to go through, you know, it's always nice to start with 1, but, you know, sometimes it'll work, sometimes it won't. 4, and this one did not. So, get your eraser out. And go back and do it again. What do we want to try next? We could try -1. And that's not going to work either. We could try, if you want to just keep going in order, you could go 2. So you're going to have 8, 7, 14, 11, 22. That ain't going to work either. Try -2. That's not going to work either. 30 what?
1/2.
Positive?
Yeah.
So 4, half of 4 is 2. And that's going to give you 1. 1 over 2. So negative 5 over 2. Negative 5 over 4. 6, that'd be 31 over 4. And 31 over 8, that didn't work. So we get those, we get those. The 1/2 didn't work. So look at what most of you are doing. You're watching. Because this is a pain. It's easier to sit there and watch. So you could try negative 1/2. And that's not going to work either. So you would just be erasing when you get there. Okay? 4, negative 1, negative 3, 9, and negative 10. Sure looks like it's 1, but it must not be. So it's got to be negative 5, 5/4. It's got to be a negative right here. It could be 5 over 4, but I don't think that seems awful close. Maybe there's. Help me here. Halves. Two minus 0.5. 28/8. We're going to be a fraction, right? Seven. Either way, it's still going to be a fraction. Okay, so you can see that we've exhausted all the ones that are around our roots. Now, you would have to go through them all in this case, and you would come up empty. What does that mean for us? No, not no solutions, because we clearly have solutions. No rational solutions. So there are no rational solutions, which means you're not going to be able to graph this. Notice what the question's asking you. Possible P over Q's, that's the red list. Okay? I want a 4. Here we go. So your P's. So you can look at this list of p's and then look at your list of q's and know that you're going to have a pretty nasty pile of numbers to deal with. Okay? Now, we're giving you a hint and telling you that 3 over 2 is one of your zeros. We just need to find one more. So your P over Q values are going to be plus or minus 1, 2, 3, 6, 7, 14, 21, and 42. That's all of these P's over 1. And then the second row of your list will be plus or minus 1/2. 2 over 2 is 1. 3 over 2. 6 over 2 is 3. 7 over 2. 14 over 2 is 7. 21 over 2. And that's it. So it's an ugly list. But they are telling you for sure that 3 over 2 is a 0. So that was nice of them to cut to a break there. So the first one that you're going to divide is 3 over 2. And you're going to be looking at 2, 5, negative 18. 2, 5, negative 18, negative 19, and 42. Okay? Now, when we do the 3 halves, you're going to get a 3, 8, 12, negative 6, negative 9, negative 28, and negative 42, giving you the 0. Here's the key. Okay? We know that positive 3 halves was a keeper. This is one of your zeros. Do not try your other P over Q's back in the original problem. You want to synthetically divide those into the quotient and get a 0 here. That means all your P over Q's that haven't worked, that have worked and you haven't tried are fair game. If you went through and you tried a whole bunch of these and they didn't work before, they're not going to work here either. Okay? If 3 doesn't go into the big number, once you find a factor of the big number, 3 won't go into that one either. Okay? So now, you're going to have to keep on with your P's and Q's. Now, it's guess and check. There's no magic way to do this. All right? Unfortunately, there's no magic way to do this. Unless you have or a graphing calculator. Because you could try right here, negative 2, and see if that works. And when we plug in negative 2 here, we have negative 4, 4, negative 8, negative 14, and lo and behold, 28. Now, you aren't going to have that luxury. You're going to have to just do guess and check until you get a winner. Once you've gotten to here, you now have 2 zeros. 3 over 2, 0, and negative 2, 0. Where are the other 2 zeros going to come from? Hang on 1 second. Where are the other 2 zeros going to come from? Factoring what? Complexity. What does this mean? These guys, the quotient. So 2x squared plus 4x minus 14, set it to 0. Anybody know?
I was just wondering why you use the first synthetic and why you use like the product of that.
Okay, hang on. When I synthetically divided the 3 halves,
Yeah, I'm not sure why you use that to plug
for here. Why did I use this quotient instead of going back to this? You can go back to this, but remember there's 4 zeros, right? One of the zeros we know, which means we know a factor of x minus 3 over 2. If you were to factor out the x minus 3 over 2, this is the other factor. Okay? So let me show you why we're doing this. If I want to prime factor the number 258, okay, I don't know how this may or may not work. Let's use one that I know will give me more factors. Like let's use 42. Okay? If I want you to find all the prime factors, give me one that goes into 42. Okay, so 7 is a prime factor, 6 is not, right? I don't want to go back up to 42 and find other prime factors. I want to now say, look, 7, you're done, you're prime. What are the factors of 6? 2 and 3. We're doing exactly the same thing when we do this. We got this original polynomial, and we're making a factor tree. One of the factors is x minus 3x. The other factor is the quotient. If we now take this and factor that down, we find out another factor, x minus 2, so the tree came down. Here's its quotient. Now I can get down to a quadratic equation, which we have the ability to either factor or quadratic formula to find the other roots. Cubics we can't do. Fourth degrees we can't do. So we never want to keep plugging back into this original when we're doing this P and Q stuff. Okay, that was an outstanding question. Never coming back here because we're just factor treeing is really what we're doing again. Okay? Somebody else had a hint too that I didn't get. -2 came out of your list of P's and Q's. I cheated. I graphed it and I looked and said, I know that this is good. We could sit here, I just don't want to spend 10 more minutes guessing and checking. You don't have that luxury. Now, I will not give you one that has 20 P's and Q's on a test or a quiz. It just takes too long. Okay? So when we get down here to this quadratic, we're going to divide everybody by 2 to start. And then what are you going to realize? It's not factorable. What does that tell you about the last 2 zeros? They're irrational. And where do we get them? They are definitely not imaginary. I mean, and I know that because we already saw the picture. But whether they are or are not imaginary, where are you going to get the other 2 zeros? Quadratic formula, or if you, in this case, wanted to, you could complete the square. And since A is a 1 and B is even, completing the square is not a bad way to go. What goes in the blanks? 1. So you have x plus 1 squared equals 8. X plus 1 equals plus or minus the square root of 8. And x equals -1 plus or minus 2 root 2. Well, those are the other 2 zeros.
Oh.
Right? -1 plus 2 root 2, comma 0. And -1 minus -1 plus 2 root 2, comma 0. And -1 minus 2 root 2, comma 0. Now those are not rational, but they're real.
So if they ask like all the solutions.
I'm probably not going to ask for that. I'm probably going to ask for all real solutions. Or I could ask for all solutions. And if they're imaginary, they're imaginary. You list them out. That just means there's an I in the answer. And sometimes with quadratic formula, that's just the way it goes. Okay. This is pretty slick as long as you can get past the fact and say, well, this is a pain, so I'm not going to do it. I'll be able to do it on a test or a quiz, but I'm not going to do it for homework. Really bad idea. And not figuring it out on your own, not practicing randomly selecting the P's and Q's, you'll only have yourself to blame, but you're going to struggle with this. So when you look at the graph, 3 over 2, 0 right here, negative 2, 0 right here, negative 1 plus 2 root 2 is right here, and negative 1 minus 2 root 2 is right here. And by the middle of next week, you'll be able to graph these as fast as the software that you're looking at right there. Okay? The graphing part is easy if you can do degree, leading coefficient, and behavior, and find the zeros. The graph of this is a piece of cake. But those of you who still don't understand degree and behavior and leading coefficient, you're in trouble. Stay after school. Come in the morning. Get caught up. Those of you who come in on Tuesday and you can't do P's and Q's, you're toast. You're toast. So please spend the time this weekend with this. Okay? This one says find all the zeros. What's on your P list? So that's not too bad, and on the Q list it's even better. We love it when leading coefficients are ones. So then you only have plus or minus 1. So your P over Q list is just the P's. So when we synthetically divide here, where is everybody going to make the mistake who makes one? Excellent observation. There's no X term. So when we're doing the synthetic division, it's negative 1, negative 4, 0, 8. And I know from experience that of the people who screw this up, 9 out of 10 of those people will not have a 0 there. And they won't even realize it because everything else works out great. We want to get a 0 right here. You want to try? 2, negative 1, negative 2, negative 6, negative 12, negative 12, not going to work. Negative 1, 2, negative 2, 4, 4, negative 8. So negative 2 is a 0. And the good thing about this one is it's cubic, so we already know that one of my roots is negative 2, 0, and I'm done with my P's and Q's. Because where are the other two going to be? They're going to be in the quotient right here. Now, look at this quotient because this is crap right here. Remember, this is equal to 0. You guys have to be smart enough to realize factoring with a leading coefficient that's negative doesn't work. What can you do? Or multiply everybody by negative 1. So if you multiply everyone by negative 1 on both sides, you get positive x squared, positive 2x, negative 4, you still get 0. Didn't help us to get it factorable because it's not factorable. Now you can complete the square quadratic formula. X equals the opposite of 2 plus or minus 2 squared minus 4 times 1 times negative 4. All that over 2 times 1. You also could have done it with the negatives up there. Okay? Negative 2 plus or minus 4 plus 16 over 2. And you've got to be able to get it all the way down to negative 2 plus or minus 2 root 5 over 2 so that you can reduce these three and get negative 1 plus or minus the square root of 5. Those are your other two roots. Are they imaginary? No, they're just not real. They're just not rational. They're irrational. But they're not imaginary. So that means negative 1 plus square root of 5 comma 0, negative 1 minus square root of 5 comma 0. Those are your three roots. And if you were to graph it, which you will later, what do we say the first one was? Negative 2, here it is. And here's negative 1 minus root 5, comma 0, and negative 1 plus square root of 5, comma 0. Those are just decimals, which you can find easily on a calculator. This P over Q thing is pretty slick. It's old school. It's not technology. Okay, it's not an iPod or an iPad or an iPhone. It's an abacus, but it works every time. Okay, this is what you're doing over the weekend. Anybody have any issues, questions?